Hello, this is chapter 21 for the astronomy class. The snoring cat from the last video has woke up, and we're talking about, in this chapter, it's going to be the evolution of galaxies over time. We did talk about the different types of galaxies before, and a little bit about active galaxies. That these are galaxies that are putting out much more energy than you'd expect. And so the way we determine the life cycle of a galaxy often correlates with the way we determine the life cycle of stars, or the way we determine uh, the life cycle of, you know, say animals that you can't keep up for their entire lives, like uh, not animals, plants, like bristlecone pines live 3,000 years. Sequoias live thousands of years. Um, you know, turtles and octopuses can be hundreds of years. Jellyfish, things like that. Things where it's not easy to tell what's going on. You look for examples of the young ones, examples of the old ones, examples of the in between aged. And so that's what we do with stars. We look for examples of newly forming stars. We look for examples of dying stars and in the main sequence ones. And we do the same thing for galaxies. And so we look and we do things like the Hubble Ultra Deep Field and other sorts of just looking at an area of the sky, and these deep observations uh, are going to end up showing us galaxies very far away, and so showing us light from young galaxies. The idea is that the light is produced when the galaxies are younger, and then they travel to us. And so seeing them at different distances is ending up showing us the different ages of galaxies. And most of our understanding is going to come from models. It's really hard to see the very earliest, right? The stuff, on this chart here, we've got a collection of young galaxies, and then the stuff before this is not observable. So we have to model some of this formation, and we have to do it based on what we think the universe looked like in this very early time we can't see. And we'll make some assumptions, or you make some assumptions. Matter is almost uniform throughout space. There are some denser regions and some less dense regions, because otherwise, there's we don't form galaxies at all. If it's nice and uniform, you just form one thing, a cloud of gas and dust. So there has to be some variation in density, and that leads to sort of a scattered filamenty sort of everything collapses down into several much denser regions. So it kind of looks like cobwebs as time goes on. You can see in this picture going from mostly uniform down to this filamenty sort of collapse. And so the first galaxies are going to be forming from these initial clouds of more dense regions. And it's going to be hydrogen and helium gas forming from these. And so they're going to form the first stars. And if you remember, we talked about these first stars, there's no heavy elements. And so the initial cloud has to radiate all its energy away from hydrogen and helium so it can contract. That means it starts with a high temperature, and that means these clouds have to be massive. And that means that you end up with massive stars. So these massive stars live a short life, they supernova early, and that initial formation is going to keep a lot of the gas from forming anything. And so you end up with gas settling down as it continues to collapse. It's going to form a disk. So why do some galaxies look like spirals and some not? Why aren't they all the same? Well, in these clouds, we figure that there's one mechanism that would allow this is that there's just not angular momentum. Is if the cloud's not rotating very much at all, it just nicely contracts and you get a spherical object. You get an elliptical galaxy. But if it is rotating significantly, then as it collapses, that angular momentum is conserved and you get a flat disk. So you end up with spirals versus ellipticals. Right? That's a possible explanation. Is maybe these clouds aren't rotating around the point they collapse around. Possibly the elliptical galaxies are denser clouds. If they're denser clouds, they form stars earlier, and so the stars form in a nice ball before the remaining material can form a disk, and so you're left with just a ball of stars. Whereas less dense clouds don't form stars as quickly, so they can get into a nice flat disk. Um, there are a number of elliptical galaxies that we can measure. Their distances are very early in the universe. I know they tend to show up as that they are significant red elliptical galaxies, is that they're not having ongoing star formation. They're elliptical because the stars that exist are survivors. They're old and red, and because there's no further collapse, there's no new star formation. So a third mechanism is collisions. All right, we can take two galaxies and they can collide together, and it makes a little bit of sense that collisions are more likely to happen in the early past because the universe is expanding. In the very early days, there would be less space, more materials packed together. There would be more opportunity for collisions. And so collisions can form these particularly weird looking galaxies, which seem to show up amongst the earliest galaxies. Of course, there will be some in later, in later ages, but the earliest galaxies tend to be more irregular, and it tends to look like examples of collisions. So one thing that shows up is when there's collisions, you're colliding two groups of gas and dust together. You're going to have a burst of star formation. You're going to see lots of young star clusters forming. You can model collisions, and the collisions can, on occasion, you can have spirals collapse. Our models show that you can take spiral galaxies and form elliptical galaxies out of them. And some elliptical galaxies are surrounded by stars in the sense that it looks like they may have formed in collisions. In particular, collisions are possible where the galaxies are close together. And some galaxies are in the center of clusters. And they seem to have consumed smaller galaxies. They've grown by absorbing other galaxies. All right, so here's where we start talking about energetic galaxies. Is that as we look further and further back in time, we notice something interesting about galaxies. In particular, some of them produce more energy than you would expect. Right? The idea is that we kind of understand how many stars are in a galaxy. It's something like 10 to the 11. And a typical star will put out energy like the sun, so 10 to the 26 watts. And so you got an idea is that a galaxy might put out 10 to the 37 watts, for example. Nice round numbers. We're getting into the point where it's kind of hard to know within an order of magnitude what's going on. But we're talking about stuff that puts out millions of times more energy, so 6 orders of magnitude more. And one type of energetic source is what's called starburst galaxies. And the idea is that the stars are forming very, very quickly. And in doing that, they're putting out a large amount of energy. And the rate at which the stars are forming implies that the supply of gas and dust get used up in a very small amount of time, less than a billion years. Because they're forming so quickly, you're getting large numbers of young, large blue stars, and so large numbers of supernova explosions, and so you get lots of galactic winds. You get lots of streams of particles moving away from the galaxy. And you can see that this is an visible light image in one picture and an X-ray image in another, showing sort of the different, you know, energetic outputs. And so some of these winds can push away additional material. So you get a formation of one of these starburst galaxies. A lot of stars form all at once, and then there's no more material. So um, another form of energetic galaxies, what's called an active galactic nuclei or active galactic nucleus. So there's different categories of these. You can look up the different categories. Um, and your text refers to one category of these as quasars, which is a contraction. It's called a quasi-stellar object. The idea is that people looked at these objects when they first discovered them, and they realized they kind of look like stars in visible light. And then you look at their energy production in radio waves, and they were massively, massively overproducing energy. Right? This is something that produces energy like a galaxy, but to us looks kind of like a star, except very far away. And so it's kind of, you know, this is something where there's some energy source that's producing lots of energy in radio waves. And so it kind of looked like a stellar object, but had this weird feature, and they named it quasi-stellar or quasar. And so ultimately, any extra bright galactic center is called an active galactic nucleus. Quasars are just the most luminous example of these. And they can produce lots of energy. They can give off materials, streaming out of them. In particular, the ones we've noticed mostly have high redshifts, which means they're very far away, and they are putting out, a trillion uh, times the energy output of the sun, but it's in a very small region, the size of our solar system or so. This sounds kind of like the problem we had with what's at the center of other galaxies, is where we have an object, we know there's a big object there, but it's from a very small space. And there's often other signs around these quasars, is that there's other galaxies that are being disturbed in some way by collisions, something. Like there's other signs that something's weird about this quasar. Quasars tend to produce lots of energy over wide uh, ranges, which means there's lots of different temperatures amongst the material. And that's kind of unusual, right? We kind of understand what stars look like and what molecular clouds look like. Having a broad spectrum like this is unusual. There's what are called radio galaxies, which put out lots of radio waves, and these radio waves are tending to come from jets of plasma from electrons that are moving at very high speeds. And so you can see here's a radio galaxy where the jets that are coming out, lobes of the galaxy, are massive. They're significantly sized. And here, plasma moving away from a galactic nuclei. All of these sorts of things, high speeds, high energies, small sizes, indicate is probably a black hole at the center of these things. Oftentimes, uh, gas and dust is going to block some of our view. So we think radio galaxies are probably kind of like quasars, except we can't see the stuff that's blocked by gas and dust. Right? So we can't make out the accretion disk around this massive black hole. So all of these things are, lots of energy over lots of wavelengths and high temperatures, lots of energetic gas and dust. My cat has just crawled up on me. And they're all coming from a very small area. This sounds like it's all powered by a black hole in some way. And in general, it's powered by the accretion of gas onto the disk, the accretion disk around a black hole and falling into the black hole. Right? That accretion gives you lots of different temperatures in the material, from gravitational energy turning to kinetic, and from friction heating the material. That heat will cause radiation, and all different temperatures will cause all different wavelengths, and the process is fairly efficient. Now, I don't have it here, but there is a video you can go look up on YouTube about converting energy or producing energy in a black hole. And generally, it's fairly efficient. You can take about 40% of the mass that interacts with a black hole and turn it to energy. Um, the interaction of the accretion disk with the magnetic field of the black hole, which should be about like the magnetic field of the star that it formed from, or from the material that it's forming from, highly compressed down because now it's from a big object to a tiny object, or it's shrunk in size. So a strong magnetic field interacting with the material will produce jets of material flying out of the accretion disk. So this is the thing. Your textbook proposes that there's some debate as to whether these exist. We've got candidates for supermassive black holes, and if you remember, we managed to make a picture of one. And if you remember looking at that, it was not impressive at the time, but the technology to even try to see it was impressive. Right? But the idea is that, in the Milky Way, we can find a location at the center of the galaxy where lots of stuff is orbiting. It implies a mass of about 4 million solar masses, and there's no visible object there. That implies it's a black hole. Other galaxies appear fairly similar. Right? This one example, the orbital speed, the distances of stuff orbiting the center of this galaxy implies 3 billion solar masses. Of course, is far enough away that we can't actually tell. We can't see it all. There's no resolution here. We can just tell that there's material moving. We can tell the speed of that material, and we can tell there's a significant amount of material in this tiny space. So we figure that probably all galaxies have some sort of black hole at their center, and it's probably it's larger than a stellar black hole. It's probably on the order of millions of solar masses. And that kind of leads us to the idea that maybe all galaxies go through this energetic phase of producing lots of energy as the accretion disk forms around a black hole. Now, of course, the accretion disk can also fall into the black hole, and so the ones that we see that don't aren't energetic, it could just be dormant. Is that these black holes have reached a quiet stage uh, after they've produced a lot of energy from the accretion disk. It seems like the masses of these central black holes correlate to the masses of the material in the bulge. And there's some sort of relationship between this black hole and how the galaxy evolved. That's one of those things where we're not altogether sure what's going on because these are very far away objects, and we're still working on the theories for that. One thing this does, because this is uh, a wide bandwidth, you have lots of different wavelengths being produced by these galaxies, by these active galactic nuclei. It lets us tell what's in between that object and the Earth, because we can look at the absorption spectrum of all the material that light passes through, and we know that it's a fairly you know, wide band. It's fairly broad in wavelength, and so we can figure out from the absorption spectrum what is in the material between the Earth and these quasars. All right, so that concludes the chapter. Basically, what I wanted you to know is that there are very energetic galaxies, and probably all galaxies were energetic at one point. It's probably due to black holes. Um, and there's a relationship between the type of galaxy and how the galaxy formed and evolved. We have some questions as to how that works, but that tends to be about, we've given you the ideas that we understand on this.